Hello, and welcome to the second part of Module 1.1, picking up with Chapter 11.3. Shown here is our now familiar setup of a mass and spring system, where the mass will slide on a frictionless surface, and the stiffness of the spring will determine how it oscillates about the equilibrium. Let's draw a force diagram again to remember what the forces are on this block. We have the force due to gravity pointing down, and the table produces an equal and opposite force, the normal force, pointing up, countering the force of gravity. So the net force in the up-down direction is 0. Now, if we took the block off and just let the spring relax, it would find a nice relaxed equilibrium. If we reconnect the block when the spring is still relaxed, the block will not move. The spring is relaxed, there is no force due to the spring on the block, and there are no other forces on the axis of the spring, the right-left axis. Thus, the net force on the block is 0, so the stable equilibrium for the block can be drawn through its center of mass. For the horizontal mass and spring system, since there are no additional forces along the same axis as the spring, the relaxed spring length will determine the block's equilibrium point. We can set our coordinate axis so that x equals 0 is located at this equilibrium point. Then the displacement of the block from equilibrium can easily be described by the x-coordinate of the center of the block. This gives us our familiar equations for the force due to the spring, F equals negative kx, and the equation of motion for the oscillating block, A equals negative k over m times x. Now let's consider the system with the hanging mass and spring. First, what does the system look like without a block? With no block hanging, the spring will also find its relaxed state, just like the horizontal spring did. Now, of course, if the spring itself does have mass, it will stretch a little bit, but we're going to assume that the mass of the spring is negligible compared to its stiffness. That is, the mass of the spring is so small that we can proceed as if the spring has no mass, and therefore its completely relaxed state has no stretch. Now we will suspend the block. If there was no gravity to pull the mass down, the equilibrium would simply be drawn through the center of the mass just like it was in the horizontal example. We could pull out our useful tool, the coordinate axis, turn it vertical, and set the 0 of this axis at the center of mass of the block. Let's go ahead and call this point y equals 0. Only now there is a force parallel to the axis of the spring. Now we have gravity. We know that gravity will pull the mass downwards, away from the spring's relaxed state. As the spring is stretched from its relaxed state, the spring starts to exert an opposing force on the mass. This opposing force is proportional to the displacement of the mass from the original unstretched length of the spring. So when the block moves away from the spring's original relaxed length, it will experience a force due to the spring, given by F equals negative ky. This means that as soon as we release the mass and the spring starts to stretch, the mass will experience two forces along the axis of the spring, the force due to gravity, F equals mg, and the force due to the spring, F equals negative ky. When the force due to the spring is equal and opposite to the force due to gravity, the net force on the block will be 0. This represents a new equilibrium that takes both forces along the vertical axis into account. This is the point where F net equals 0 for the block. So this is actually the equilibrium point for the block, even though the spring itself is stretched and not relaxed. To keep track of things, we're going to go ahead and label this particular y-coordinate, the delta S from the original relaxed length of the spring, y equals d. So the stable equilibrium for the block is where the force of the spring equals negative kd. Since the net force is 0 at this new equilibrium, we can see that at this point, mg equals kd. Now, the block may very well keep moving once we've dropped it from the relaxed spring straight. It'll pass through the equilibrium, it'll keep going down for a while, but the specific point where mg equals kd will remain the same, and the point where the spring is at its original relaxed equilibrium will remain the same. So the quantity d does not change no matter how the block moves. This means that the quantities mass, the acceleration due to gravity, g, the spring constant or force constant, k, And D, the distance between the unstretched spring length and the point where F net on the block equals 0 are all constant quantities. So the block will now oscillate around the point where the net force is 0. In other words, where we have set y equals d. Describing the mass's motion would now be a whole lot easier if we had originally set the 0 of the coordinate axis at y equals d, instead of at the relaxed length of the spring. But that's okay, we can fix this. If you think of the coordinate axis as just a tool, like a meter stick, then we can set our meter stick down anywhere, and we can go get a second meter stick and set that down anywhere. So we set our y meter stick down and marked its 0 point where the spring is relaxed, but we can go get another meter stick, call it the z meter stick, and align this one so that the equilibrium is at z equals 0. Both meter sticks are still vertical, they've just got their 0 points lined up at different points. So now we can write out Hooke's law for this vertical mass on spring system, and we're going to go ahead and choose the z meter stick, where z equals 0 corresponds to the equilibrium of the block, and now delta S is just simply your z coordinate, so F equals negative kz. In a way, writing it like this just ignores the force of gravity, and it ignores the upward component of the spring force, F equals negative kd, because those two parts of the force cancel each other out anyways. This is kind of the same way that we ignored the force of gravity and the normal force in the horizontal spring, only now we're ignoring two parts of the force that are on the same axis as the spring. Okay, so to keep track of all of the forces that we've been talking about, let's draw a force diagram for the block. We have the force of gravity equals mg, and that points downwards. We have the force of the spring due to the stretch between the block equilibrium and the relaxed state of the spring, and we decided that this was given by F equals negative kd. And then finally, we have the force due to the oscillation of the mass around the block's equilibrium, and this is given by F equals negative kz. The net force on the block at any time, then, is the sum of all of these forces. F net equals mg minus kd minus kz, just like equation 11.4 in the textbook. Since we also know that the net force on the block can be just as well described by F equals ma, we can set ma equal to mg minus kd minus kz. And since mg minus kd is just 0, this returns us to our familiar equation of motion, a equals negative k over m times z. This whole setup just shows that no matter how many forces are at play and how they are oriented, the block on the spring will oscillate around the point where the net force on the block is 0, and it will oscillate around that point as if there are no other forces involved. If a fresh coordinate axis is drawn at that point where the net force on the block is 0, we can label it however we want, and the motion of the block can always just be described as a equals negative k over m times the displacement, where the displacement is measured along our chosen coordinate axis. So you could say that simple harmonic motion is simple because no matter how many forces are at play, the motion acts as if there is only one force, the force that restores the object to its stable equilibrium. In physics, we are very interested with the motion of objects. In particular, if we can understand the motion of an object fully, we can actually make predictions about future motion. Alternately, we can understand how an object moved in the past, even if we weren't there to personally witness it or measure it. Two very important quantities that you have learned that give us information about an object's motion are velocity and acceleration. Velocity tells us how much distance the object will cover in a given period of time, and acceleration tells us how an object's velocity changes over time. An equation that gives a relationship between an object's position and some component of its motion, either velocity or acceleration, or sometimes both, is called an equation of motion. Equation 11.3 is the equation of motion for objects moving with simple harmonic motion. It turns out calculus can take equation 11.3 and tell us the time it will take for the block to accelerate and decelerate through one complete cycle. This is a quantity we defined in module 1.1a as the period. You'll have to take calculus's word for it. The formula that you get for the period of an object oscillating according to equation 11.3 is just this. T equals 2 pi square root of m over k. Of course, this class is algebra-based physics, so we won't go into the calculus used to get this result. I can point out, however, that since m and k are constants, they just ride along as passengers, so it should not be too surprising to see that the fraction k over m appears in both equations, although it is inverted for the period to m over k. Since we know that the plot of position versus time, similar to figure 11.4, can be described by either a sine or a cosine, and we know that sines and cosines split a cycle up into 2 pi radians, it should also not be too surprising to see the 2 pi creeping into our formula for the period. As the textbook emphasizes, the period is not dependent on the amplitude. One way to look at it is to look at a plot like this, where there are several oscillations and each oscillation has a different amplitude, but they all have the same period. So clearly, the period cannot be dependent on amplitude. Still, for a lot of people, the fact that the period is not dependent on amplitude can be counterintuitive. One way to try to understand this is by going back to equation 11.5. You notice that if we increase z, we have to increase the acceleration a by the same amount, since k and m are just constants. So if you pull the mass further away from the equilibrium point, that is, if you increase z, the mass will then have to accelerate back towards the equilibrium at a proportionally greater rate. If we did a series of experiments pulling the mass to different positions and measuring the acceleration compared to the position, we could create a table. The first time, we shouldn't pull the block down very far, so the force on it and therefore its acceleration is kind of slow. The next time, we'll pull it down twice as far. Its initial position is then twice the initial position from before. This means that the initial force on the block doubles, and it also means that the acceleration of the block will double. Notice that no matter what you multiply the position by, that is, no matter how far you pull the mass down before releasing, the change in acceleration exactly matches the change in position, bringing you right back to the same equation 11.5. So when we use that magical calculus on equation 11.5 to get the formula for the period, any change in the amplitude will cancel out with a corresponding change in the acceleration, no matter how far the block is pulled down before releasing. So the end result is that the period of oscillation does not depend on the amplitude. Let's return to our two examples of a mass and spring system, the horizontal mass and spring system and the vertical mass on spring system. What are some of the assumptions that we made for these systems? For the horizontal system, we assumed the tabletop was frictionless, the spring was massless, there is no air resistance, no heat was lost through the stretching and compressing of the chemical and molecular bonds within the spring, and the spring retains a constant spring constant. It does not get stretched over time, losing its spring stiffness. For the vertical system, we make similar assumptions. All of these assumptions make physics easier, and we like to make physics easier. But these assumptions all have something else in common. The things that we assume to be negligible are the same things that cause the system to lose energy. Friction causes heat to be released, carrying energy away from the system. If a spring had mass, then its stretching and compressing would involve a fluctuating kinetic energy associated with the spring. Air resistance sucks energy out of the system in order to push the air molecules out of the way. So assuming that these things are negligible makes things simpler because it means that energy is conserved. We're not losing energy through any of these other things. Then we only have to think about two components of total mechanical energy of the system: the potential energy stored in the spring and the kinetic energy of the block. The formula for the kinetic energy of the block should be familiar to you. Kinetic energy equals 1/2 mv squared. You may or may not be familiar with the potential energy stored in a spring. It is covered in Chapter 7 of the textbook, but if you want, you can just trust that the correct formula is potential energy equals 1/2 k delta S squared. Now, if we use the same convention of setting the zero of our axis at the equilibrium of the oscillation, this formula just becomes PE equals 1/2 kx squared. Notice that the kinetic energy is associated with the actual movement of the block, the velocity, as well as its mass, while the potential energy is associated with the spring constant and the position of the block. The total mechanical energy then is E equals kinetic energy plus potential energy, or E equals 1/2 mv squared plus 1/2 kx squared. We notice that when the potential energy is 0, the total energy just equals the kinetic energy. Similarly, when the kinetic energy is 0, the total energy just equals the potential energy. So when is the kinetic energy 0? The kinetic energy is 0 just as the mass reaches the peak of its oscillation, just when it is switching directions. This happens, of course, when the position is equal to the amplitude, x equals a. So at this point in time, the total energy just equals 1/2 Ka squared. Since energy is conserved, we know that the total energy must always equal 1/2 Ka squared, even when the kinetic energy is not 0. So we could also write 1/2 Ka squared equals 1/2 mv squared plus 1/2 kx squared. These equations, along with equation 11.3, 11.6, and 11.2, give us multiple ways to relate all of the key quantities involved in simple harmonic motion. Your task is to determine which variables you are given, which variables you need, and how to manipulate the equations to get to your answer. Example 11.5 gives you the mass, the period, and the amplitude, and it asks you to find the maximum acceleration and the maximum speed. Example 11.6 asks you to continue on to find the velocity of the block at a specific position. You should make sure you understand these examples and can apply the concepts to similar problems. Every chapter in the textbook has a summary page at the end. This summary has a list of things that you should have learned. The summary for Chapter 11 is on page 220. It is good practice to read through this list and honestly assess if you have learned everything that you should from this chapter, because we will be using all of these concepts again.